In this video for VCE Algorithmics students, I cover proof by induction. This is one of the hardest concepts in algorithmics and mathematics at VCE level to get your head around, so expect to want to watch this video over a few times, giving yourself a chance to think it all through. Unlike VCE and mathematics, we will focus our proofs on strong induction rather than weak induction, and we will be doing graph theories rather than numerical theories. We'll start with a reminder of weak induction, and you may not be doing specialist maths, so you may have never seen weak induction before. The idea is more or less the same as for strong induction, but for a important difference, which I will cover. So the general approach is we want to prove a statement is true for all integers, but we can't do it directly. Instead, we first show that a statement is true for a base case. Then we prove that if it is true for one item, then it must be true for the next item. It's a kind of conditional statement, so we're not saying it's true for anything, we're just saying this causal connection holds. If it's true for one thing, then it's true for the next thing. So if it's true for the kth item, it must be true for the k plus 1th item. That's where we're going to spend the bulk of our work proving that implication. Now, since we've shown it's true for n equals 1, we can assume it must be true for n equals 2. I started at 0 there, doesn't matter. And if it's true for 1, then it's true for 2 must be true for 3 true for 4 true for 5, and so on. We don't actually have to do this, but the logic behind the process means that it's therefore true for all natural numbers in this case. So let's see how this looks. We will start by proving that the sum of the first powers of 2, so up to 2 to the n minus 1, is equal to 2 to the power of n minus 1. That is where n is a natural number. We start with n equals 1. These are usually quite easy. Note the way I'm setting it out. I don't want to see a sentence like 1 equals 1. We say left-hand side equals 1, because it's just the first 1 before the 1 plus 2 plus 4. The right-hand side equals 2 to the 1 minus 1 equals 1, which is the left-hand side. So make sure we're saying left-hand side equals this, right-hand side equals this, which is also the left-hand side. Therefore, true for n equals 1. There's often not very much work to do there, but it's very important that we state those base cases. The next bit, we must assume it's true for n equals k. So 1 plus 2 plus 4, blah, 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 up to 2 to the k minus 1 equals 2 to the k minus 1. So we're assuming that's true. And I find it helpful to then set out the thing you're going to try to prove, which is if for k plus 1, then the statement is also true. So hopefully you can see how now we're going up on the left-hand side to k instead of k minus 1, which is actually k plus 1 instead of k, because the theorem was n minus 1. And then on the right-hand side, we've replaced k with k plus 1. Now again, very important, you do not get to work on both sides of the equals side here. We have to say a left-hand side equals something, and what I've done straight away is replaced this part of the left-hand side with this thing here. That was our inductive hypothesis from the line assume true. Now we just need to have a sense of algebra, and we're keeping our eye on the prize. We keep looking at 2 to the k plus 1 minus 1, and we just have to have seen enough algebra to figure out some strategies here. We can see we've got lots of 2 to the k, which using our powers of indices, laws of indices, we make that 2 to the k plus 1 minus 1, which is what we wanted. Hence, true for all natural numbers by mathematical induction. The way they like you to set this out in Spec, that final statement is a little bit more formal. In algorithmics, you can be less formal. Right, number 2. This is quite a chunky example. Pause and read through. I think if you write it out, it's much easier to see what's going on here. Base case, n equals 1. That is just 1 squared, which is 1. On the right-hand side, we can sub 1 in, and we end up with 1 as well. So we know our theorem here is true for n equals 1. Now, our assumption is that this is true for n equals k. And we are going to show that it's true for k plus 1. So you can see on the left-hand side, the blue part is the inductive hypothesis, and then I've added in the red part, which is the extra bit for the summation on the left, and then the right-hand side is all the k's in the right hand side of the assumption replaced with k plus 1. Got to pause this, make sure you like check that you understand what's happening here. And I would suggest pause it and try it out, because I was going through my textbooks to find a fun theorem. I thought this one was really fun. So once again, we use our inductive hypothesis. And now ideally we want to avoid expanding and refactorizing. Sometimes people expand like some awful bunch of quartic stuff. What we're doing is keeping our eyes on the prize, and we can see that the right hand side we're aiming for starts with a half bracket minus 1 close bracket to the k. So let's factorize that out of the blue and the red terms. And you can see, I think, to get minus 1 to the k minus 1, we need to times it by minus 1 to the minus 1, which, by the way, is just minus 1, because anything to the minus 1 is 1 divided by something, and 1 divided by minus 1 is minus 1, times k plus 1, and then we need to times, to get to the red term, we've got to times by 2 to get rid of the half, and the minus 1 to the power of k is already there, so then we just have k plus 1 squared. Now we look within those curly braces, and we can see we can factorize k plus 1 out of this term and this term. So we take the k plus 1 out, and we're left with that minus 1, which I told you where that came from, and k, and then we've got rid of one of the k plus 1s on the right-hand box. And from here, it's just a fairly simple bit of expanding and collecting those very simple like terms, which gives us the right-hand side, hence true for all natural numbers by mathematical induction. Alrighty, let's see this happen with graph theory. A fairly simple graph, one which I tend to just show is intuitively plausible in class. We are going to prove that every tree with n vertices has n minus 1 edges. Our base case, we're going to have one vertex, and that's just a single vertex with no edges, because we can't have loops in simple graphs, so it must be true, which feels sometimes a bit unsatisfying, but we've got to say it, and we've got to try and give some sort of supporting reason. Now we assume it's true for n equals k, so a tree with k vertices has k minus 1 edges, and we want to show that for a tree with k plus 1 vertices, that has k edges. Here's the way we're going to do that. We are going to consider a tree with k plus 1 vertices, and any tree with at least 2 vertices must have at least one leaf node. Now this we haven't really proved properly here. It can be proved, but hopefully you can see how that's kind of intuitively plausible, because if it didn't, there would have to be a cycle. So there's got to be at least one leaf node. And we shall remove that leaf node and its corresponding edge. So we've now gone from a graph with k plus 1 vertices to a graph with k vertices. Now, that graph with k vertices, by our inductive assumption, has k plus 1 edges. When we add the vertex back in, we now have k plus 1 vertices and k edges, because we've added 1 to each of them, and that is what we were aiming to get. Hence, our statement is true by mathematical induction. We're going to consider the same proof now using strong induction. So let's just explain what the difference is. For weak induction, we assume that something is true for n equals k, and we consider k plus 1. For strong induction, we assume that something is true for all values of n less than or equal to k. Okay, hopefully we'll see how this works out. So once again, we're going to prove that every tree with n vertices has n minus 1 edges. Our base case is exactly the same. And now we are assuming all trees with n is less than or equal to k vertices have n minus 1 edges. And now let's consider the tree with k plus 1 vertices, and we will show that it has k edges. Here's a tree, and sometimes when we're doing these diagrams, I find it helpful to draw these. Like, obviously this is just one example, it's not a proof, but it can help you clarify your thinking, and also can show the examiner what's going on a little bit as well. So we are going to remove any node, and for the purpose of this, I'm going to remove this one. Now that node has m edges. It must have at least one edge. So we've got rid of that node, and in this case it's got 3, but we've got m edges have been removed. And what we end up with is a set of m components, each with up to k vertices. So what you can see here, we've got a component over here, or a subgraph. We've got one over here, and we've got one over here. Now, by our inductive hypothesis, the number of edges across all of the components is k minus m. Well, why is that? We know there are k vertices altogether, and each time there's a separate component, we have to take away one edge, because let's say there's, you can see I've got 3 components, there must be 2 edges between them. If there were 10, there would be 9. And so every time there's a new component, we have to take away one edge. There are m components, so we need to take away m edges. So that is how we use our inductive hypothesis. Now we will add that vertex back in. So there we go. And now we've gone back up to k plus 1 vertices, and we've added in the m edges that were connecting that vertex. Let's just highlight that vertex again. We had those 1, 2, 3 edges connecting it. And so now we end up with k edges, which is what we wanted. Hence, true for all numbers of edges using mathematical induction. This might feel like overkill for this proof, but it does avoid having to prove that a leaf node always exists, and it's also to show you the difference between weak and strong induction. So we had to assume that our statement was true for all n less than or equal to k, because we're breaking our graph down into lots of smaller graphs, and it's quite arbitrary. There's not an obvious sequence of numbers that we're working through. When we were doing all natural numbers, it's kind of obvious. We do 1, then 2, then 3, then 4. Graphs aren't built up in such an obvious way. So we have to prove that it's true for all subgraphs, or whatever it is. Let's see how this works on another theorem, which is that every graph with at least 2 vertices has at least 2 non-cut vertices. So a non-cut vertex is one that you can remove without disconnecting the graph. So we take our base case, n equals 2. There are 2 vertices. It could be an edge between them. There might not be. Removing either vertex leaves just the other. So neither vertex is a cut vertex, because when you remove it, you haven't disconnected the graph. You're still left with the rest of the graph is still connected because it's only one vertex. So true for n equals 2. Now we assume that our theorem is true for all graphs with less than or equal to k vertices, and hence we will show it's true for k plus 1 vertices. So let's imagine our graph with k plus 1 vertices. In fact, I will draw another little graph to help us out. If there are no cut vertices, then since this graph has k plus 1, which is more than 2, then the theorem must be true. Now, if there's one cut vertex, we shall remove it. So let's do that here. We shall remove this one, just for illustrative purposes. We are left with m components, at least 2 components of this thing. It couldn't be 1, because otherwise, if it was 1, then it wouldn't be a cut vertex. It would be a leaf node. So we've got this one component here, one component here, and one component here. So for each component, we're going to consider that component with the removed vertex replaced. So let's just think about this top one. So this component with the removed vertex replaced, we know because it has a maximum of k vertices, because we've already got rid of some of the other ones, then there must be at least 2 non-cut vertices within that component. And one of those must be not the one that we just removed or replaced. And so one of those vertices, if we were to remove it, that component would not become disconnected. And since it wasn't involved in connecting that component to the main graph, it's not going to disconnect the whole graph either. The one we just re-included would, but that doesn't matter because there's a second one. Now, each of the m components contains at least one non-cut vertex for the whole graph. So when we re-add the cut vertex we removed, we must be left with at least 2 non-cut vertices. Hence our theorem is true by mathematical induction. Now, let me start by saying I don't think you'd get a question quite this hard in an exam, and I have tried to express this proof in a way that's accessible, and in doing so, I'm pretty sure I've oversimplified, made it a bit hand wavy, but hopefully we can see how this differs to weak induction. We can't just consider the previous case because there's no obvious previous case, there's no sequential order, but we can split this down into two or more graphs, and we know that our theorem is true for all of those. So common mistakes you might make with this, we might, for example, assume that a cut vertex splits the graph into two, or that we end up with two graphs with at least two vertices, whereas in fact we could end up with a leaf node, for example, although that wasn't a problem in this case, so sometimes we have to consider that. Anyway, as I say, I think this question is probably a bit beyond what you would get. The last time we saw a really nice version of this was in 2023. Have a look at this. It's question 4. I'm not going to go through the first couple of bits where we just look at the like some definitional stuff that leads you into it. Next, we're given some code to interpret on graphs that have had every edge made randomly directional. Complete graphs with every edge has been randomly made directional one way or the other. So we scan through the code and we can see there's a base case and some recursive calls. So clear we have a recursive algorithm. Hooray. It's a good idea to try this on a particular node anyway to see how it works. But in fact, what they have asked us to do in this question down here is to consider that. What happens if A is selected in line 5 here? So we select the node A randomly and we create a set of all the nodes going into A. So we'd say that V in would be the set of just F, and V out is going to be B, C, D, and E. B, C, D, E. And what we are going to have to do is show by induction that every class of graphs contains a path containing every node. And the way I've treated this is that the code needs to generate that for us. If we can show the code generates it, then we know that that path exists. So first off, we consider our base case. Lines 1 and 2 give us an empty path when n equals 0. And if n equals 1, we get a single node path as required. Next, we are going to assume this is true for all graphs with at most k vertices. And we're going to consider a graph with k plus 1 vertices. So we work through the code. Line 5 chooses a random node, leaving k vertices, to be split then between two subgraphs, the v in and the v out, and the largest either of those could have is going to be k vertices. So in the previous one, let's just skip back, we can see that we had ABC, so 6 vertices. We removed one of them, giving us 5, so that's like going from k plus 1 to k. We were left with 1 and 4. If we'd chosen, is there one with, let's say we chose, no, there's not one with all in. It's possible we could have had an empty set and then all of them in the other set. By our inductive assumption, for each of those subsets, the code will return a path through all of those vertices. And then line 12 will create a path through the first set, then the random vertex we chose in line 5, and then the second set, completing a path through k plus 1 vertices. Hence, there is a path for all graphs using strong induction. Again, note how this problem looked a lot like the last one. We're not trying to go back to one previous case, and they really have set it up here nicely so that you can follow the structure you've been given. So, like in any algorithmics exam or any maths exam, consider the previous part, see if it's trying to help you work out the next part. Hopefully, from all this, you can see how to apply some induction to graph theory and the importance of using strong induction rather than weak induction.